The question here is, could you do an example on determining the combined stresses? In this particular example, I'm going to show you how to combine stresses due to the axial force N, the bending moment M, and the shear force B. This is the problem that I have chosen here. We have a beam that is bent at B. The beam is supported on a roller at A and a pin at point E. We have two types of external forces here. A distributed load that goes from 0 to 5 kilonewton per meter at this point right there. And then we have a point load acting vertically down. The magnitude of the point load is 10 kilonewton. The beam has a constant trapezoidal shaped cross-section throughout. And the question is to determine the combined stresses at points C and F and show on suitable differential element. The cross-section is taken at point D. In a broader sense, these are the steps. Step 1, determine the internal forces at point D. We're going to find that there's going to be an axial force, bending moment, and a shear force. Step 2, determine the stresses at C and F due to each of these internal forces, N, M, and V, and then we combine them in a suitable manner. If you recall, the axial force N produces a normal stress sigma, which is given by N over A, where N is the axial force, A is the cross-sectional area of the section. The bending moment M produces a normal stress, and it's calculated using this bending formula, sigma equals my over I, where y is the distance measured from the centroid in the y direction. I is the second moment of inertia of the cross-section about the z-axis. The stress due to the shear force V is the shear stress given by VQ over IT. We'll define each of these terms more precisely in a little bit. So coming back to the major steps, what I like to do here is to focus on combining the stresses. I will not spend time on step number 1. Hopefully you guys are pretty good at that by now, but I'll leave the details here so you can follow. Here's a section on finding the support reaction. There are 3 support reactions, Na, Ex, and Ey. You need 3 equations. So I took a moment equation about point E, and that's this first equation. That gave me a value of 6.3839 kilonewton for Na. And then I summed up the forces in the horizontal direction, and that gave me a value of 0.96 kilonewton for Ex. And then I summed up the forces in the vertical direction. That gave me a value of 10.56 kilonewton for Ey. Here is the section on finding the internal forces. So what I did was I sectioned the beam at point D and considered the equilibrium of the right side, which is this. There are 3 internal forces to be found, and therefore we need 3 equations. And these are my 3 equations. Some of the forces in the x direction equals 0, some of the forces in the y direction equals 0, and some of the moments about point D is 0. I found my internal forces from these 3 equations. Step number 3 is to go ahead and find the stress due to each of the internal forces. As part of that, we need to do a number of things. Firstly, we notice that the cross-section we have is symmetric about the y-axis but not about the z-axis. Therefore, we don't know exactly where the centroid of the section is on the y-axis. In this section, I'm finding the distance y bar to the centroid C measured from this line GH in the y direction. Once again, I'll leave the details here so you can follow through. The value that I got is 61.54 millimeter. In other words, this distance right here is 61.54 millimeter. The next thing we want to do is to find the second moment of inertia of the cross-section about the z-axis. We follow the approach we normally take for composite sections here. I divide the cross-section into 3 sub-areas of standard shapes. This triangle 1, this rectangle 2, and this triangle 3. And here are the standard formulas for the second moment of inertia of these shapes about an axis that passes through the centroid. Since here the centroids of the subareas don't coincide with the centroid of the cross-section, we need to use the parallel axis theorem in order to find the second moment of inertia about this global axis Z. And here is the parallel axis theorem. I'll let you follow through the details here. The value that I got is 16.515 times 10 to the 6 millimeter to the power of 4, which is also 16.515 times 10 to the minus 6 meter to the power of 4. The next thing we want to do is to calculate the values of capital Q's for the 2 points we are interested in calculating the stresses at, which are point C and F. We need Q's to calculate the shear stress due to the shear force. So what do? We draw a line parallel to the Z-axis through the point of interest, thereby subdividing the section into 2 parts. Then use one of those parts to calculate the Q. And here is the definition of the Q, and in this column I'm calculating the Q for point C, and in this column I'm calculating the Q for point F. These are the values that I got for Q's for these points. Now that we have done all the preliminaries, we can go ahead and calculate the stress due to each individual force and then combine them. Let's start with the simpler one, stress due to the axial force N. Firstly, the stress due to the axial force is going to be a normal stress. It's going to be acting on the x-plane in the x direction, so I'll call this sigma xx. Second, we know that the stress across the cross-section is uniform, and therefore the stress at point C and the stress at point F are equal to each other. Magnitude, of course, is force divided by the cross-sectional area. The force is 0.96 kilonewton, and the area is 9.75 times 10 to the minus 3 meters squared. So that gives us a stress of 98.46 kilopascal. We also note that this is a tensile stress because the force is a tensile force and therefore the stress is a tensile stress. Next, we calculate the stress due to the bending moment M. Since point C is the centroid, the stress on that is 0. The bending stress at point F, using this formula My over I, is 6394.3 kilopascal. And you can see from the direction of the bending moment, since point F is above the neutral axis, the stress is going to be a compressive stress. Finally, we calculate the stress due to the shear force V. We know that the shear force produces a shear stress, and this is the shear stress on the x-plane in the y direction. So I'll call this as tau xy. And here are my calculations for the stress at point C and point F. We get a value of 1536.1 kilopascal at point C and 1631.1 kilopascal at point F. You may want to note that the stress at point F is actually greater than the stress at point C. Now this is due to the non-symmetric nature of the cross-section. You might recall for a rectangular cross-section, the maximum always happens on the centroid. In this slide, we combine the stresses. Here's a summary of the stresses due to individual forces from the previous slides. We note 2 things here. Number 1, sigma xx is produced by 2 different sources, the axial force N and the bending moment M. On the other hand, the shear stress is produced only by the shear force V. So here we combine the normal stresses, keeping in mind the signs. At point C, the bending stress is 0, whereas the stress due to the axial force is 98.46 kilopascal, which is a tension. At point F, however, we have both. We have a compressive stress of 6394.3 kilopascal due to the bending moment, whereas we have a tensile stress of 98.46 kilopascal due to the axial force. So you combine the two with a different sign for each, and we get this value. So the net here is a compressive stress. The combined shear stress, of course, is the same as the individual shear stress, so I kind of copied that over here. So here are the differential elements at the 2 points, point C and F, showing all of the stress components.